Thank you, Scott, and thank you everybody for attending. As Scott mentioned, I kind of wear at least two hats on most days. I have river forward exploration, have activity in the Bakken play in Montana and North Dakota. We have some acreage and some production in the Scoop Stack Merge play in Oklahoma, and most of our focus now is in the southern Delaware Basin. River Forward helped open up that play originally in the 2008-2009 timeframe and has remained active in there. Then the other most important hat for everybody else in the world is the relationship with the University of Texas and the Bureau of Economic Geology. For the past 2 years, I've been managing the Torah program, and Torah is, well, when I first heard that, and most people hear that are my age, they think of the movie Torah, Torah, Torah. I always thought that meant war, war, war. Then the Japanese said that before they went off their air carriers going into Pearl Harbor. And they did say Torah, Torah, Torah going off those carriers, but it actually means tiger, tiger, tiger. I was corrected by a Japanese student on the meaning of that, so I appreciate him letting me know what that really means. But for us, it means tight oil, and I'll put it in parentheses, and gas resource assessment. And so we'll look at that a little bit. And what we're going to talk about today is mostly my other life, that most people in oil and gas that I've had contact with haven't seen this type of presentation before for me, because we're usually talking about how we build geomodels and how we're using that in unconventional resource plays at the Bureau. Well, so today we'll spend as an introduction kind of a little bit on what Torah is, and then we're quickly going to jump into macroeconomics, finance, on what unconventional resources have done worldwide and the domestic impact. The meat of what we're talking about is number 3 there, the perfect unconventional resource portfolio, construction, the results, and then I'm going to give you some more good news at the very end, how to use those models and the trends that we're kind of seeing in unconventional resources. So what is Torah? Well, Torah is at the Bureau of Economic Geology. It's an industrial consortium sponsored by these companies, and more we hope all the time. I had some good friends at the lunch table that we'll be meeting with next week. It's going towards companies that you see on that list that are the Permian Basin specific players, some of the service companies, investment banks, private equity firms, and just recently more and more going towards the large companies, Exxon, Shell, Total. Total was one of the original members. Exxon and Shell are new members there, and that's the direction that unconventional resource play is going. And so everything behind what I show today is actually built on the shoulders of all these people. These are the really smart people at the Bureau, mostly PhDs in their various subject areas, all the way from petrophysics and stratigraphy, in engineering, in physics, and economics and statistics. And normally what Torah does, and this is the workflow of our project, we'll start at the upper left. If you Google Wolfcampian for Permian Basin, typically about 70% of the papers that first show up are going to be Steve Ruppel, they're going to be Scott Hamlin, and others at the Bureau have been working that stratigraphy for years. And of course we have probably more rock than anybody else in the U.S., especially in the Permian Basin side of it. And so we start with those stratigraphers, and so the upper left, we're just starting with a quartz, carbonate, illite variables that are plotted there that stratigraphers came up with, because the next plot is the petrophysicist. Now, we don't let the petrophysicists start doing their models until they go out to the core warehouse with the stratigraphers and understand what the rock's really telling them. And then they can go back and start working on those models, and they have to work around the areas where we have that core so that they show that they can match on their quartz, carbonate, illite diagram, essentially the same thing, and those are the wells immediately around the cores that you see on the left. That information is all entered into Petrel. Our geologists are picking tops in thousands of wells throughout the Permian Basin and the other resource plays. They're doing that typically in Petra, and then we bring that over into Petrel also, and then we end up with a two-dimensional look of the basin, and that's a cross-section of the entire Sprayberry Wolfcampian interval, about 3,000 feet. Over on the left, the west-hand side, coming off the Central Basin Platform, dropping down into the middle basin, and then on the right-hand side going onto the eastern shelf. So you can see the carbonate influence of the Central Basin Platform and the Wolfcamp in the lower left portion of that. Then you can see a carbonate influence coming in from the eastern shelf in the Sprayberry intervals, and then that brown organic rich mudstone that fills up most of the middle of the basin and makes the resource play. Well, we finally take that into Petrel. I'm down in the lower left now, because we don't want to look at this in just the 2D world, either in cross-section or map view. We do this all in the 3D world, and so we're taking typically about 36 geologic and reservoir engineering parameters. The reservoir engineering parameters could be reservoir/geologic, because it's initial pressure. It's the state of the rock before man does anything to it. So what's there in place? Because what we're going to answer is how much oil is in place, how much can technically be recovered, and then finally how much can economically be recovered. We do the history matching, we do statistical modeling with all those parameters back to the production data information, and then we finally look forward and do some production outlooks looking forward. So that's kind of what it is. And we're looking at the Midland Basin here. We're on the southeast. We're kind of looking to the northeast. You can see up on the upper portion of that, there's a indentation coming into the Midland Basin. That's the Glasscock Arch, for those of you that work that area. And that is a porosity model. And our grids in the Midland Basin are 3 to 5 foot vertically, 500 feet by 500 feet. That generates over 1 billion cells. Those billion cells each have about 30 variables in them. And thank goodness we have a supercomputer, because then we can go back and start doing the modeling that we want to do. And the whole idea is that we're adding all those variables together. We're letting the computers help us with doing that. And so the first question we're answering is in the lower right, what's the original oil in place? And then we can start looking at taking it out. But we want to know geologically what's there first. I always call that what God gave you. What's that state before I ever put the influence of what do we do engineering-wise when we drill a well and then we frack and complete it? Because those things, you might be an A rock, but you might get a C completion. If you get a B result and you haven't done that kind of work grassroots up. So there's a lot of work that's being done out there that looks at results. And statistically, their statistical answer is very tight, but they can't tell you the reason why unless you do this kind of ground floor workup. So let me just kind of show you some results that have been reported. This is from last year's fall meeting. What's on the left is a typical distribution we look at of what the modeled cumulatives were for the Wolfcampian A in this case versus the model. You can see that's pretty tight plot. But I really love Svetlana Konakova started these maps over on the right-hand side. And what this heat map shows is the heat map is the model, and the little dots you see are the actual well results. Well, there are 5,600 actual results on this map. How many dots do you see? Maybe 100 or 200 dots, right? So where you see a dot, it's because the color of the dot is different than what the model says. So what you're seeing is where the high variability is. So all the dots you don't see, it means it's blended in with the background, and the model did a very good job predicting the results. And this is 6 months cum per 1,000 feet of lateral is what we're showing there. This one is the one I always use because this study was completed in 2016. We're redoing the Eagle Ford. We'll present that at Torah's fall meeting. Again, the heat map, when we do these heat maps, we do them at different economic scenarios. You can see on the key there that I've highlighted in red, this is the $50 per barrel oil heat map. And that was generated in 2016, predicting within a mile where each well would be drilled within 1 mile in the Eagle Ford play. And so you can see from the key there, it ranges from a 0.1 to a 1.3. Well, that means there's a 10% probability within that mile a well would get drilled, up to a 1.3 or 1.3 wells would get drilled per square mile. And the dots are the actual wells that were drilled during 2017, 2018. I use $50 per barrel because that's kind of the average over that period of time. And there's an 80 to 85% correlation between where we predicted wells would get drilled down to a mile level and where those wells were actually drilled. Once service companies started seeing this, Covia, one of the largest sand suppliers, saw this and they said, you mean you predicted in 2016 with 80% accuracy where wells were going to get drilled on the 1 mile in the Eagle Ford play? And that's right. This is the only map they needed to go back to their management and said, we need to be involved in this study. This is up in the Bakken. This was a real one. Let's start on the right-hand map. The right-hand heat map is predicting where wells are going to get drilled, again, down to the mile level. And I have 2 squares outlined there because I said, okay, I'm going to test this myself as well as test this anecdotally. And that's because that's where River Ford, my company, has acreage. And so over in that yellow box, you can see that that's a very cool colors, and it was predicted that no wells would get drilled in that yellow box. And I have 24 producing wells in there, but no new wells were drilled within that box. Now, you say, well, that's a good area. Yeah, you're right, but all the well, basically, that's been drilled on a cell or a cube kind of basis already, so most of the wells that need to get drilled are drilled. The other red box on the right over there is Elm Coulee Field, and it's a little bit hotter, as you can see, and it's showing in some of those red areas that 0.25 wells would get drilled in that area per square mile. And Elm Coulee was the first discovery. When it was discovered, it was the largest field found in the United States in the last 56 years, found around the 2000 time frame. But it's predicting that some additional wells will get drilled over there. Well, it wasn't drilled as densely. There's generally about 2 wells per square mile there. And indeed, we actually drilled some wells over there. We'll see some of those results. And it matched very closely with what was predicted. 0.25 was predicted, and 0.25 per square mile were drilled. So we have several sections, drilled 2 wells, and the averages came out right up where they should have. The map on the left is, again, predicting what the 6-month cumes would be per 1,000 feet. It was predicting that my results in that area would be 10,000 barrels of oil per 1,000 feet drilled, and the actual results were 11,500, so within about 10% of what was predicted. So some very good predictions of what Torah has done. So that's the overview of what Torah has done. If you haven't seen the Torah presentation before, please get in contact with me. I'd love to come over and show it to you because there's a lot of great detailed geology that goes into that. So let's look at the economic impact of unconventional resources. And this is the production curve for the United States going back from January of 1920 until about 2 months ago. Most recent information I had from the EIA. You can see that we were just over 1 million barrels a day in 2020. That climbed relatively steadily until 1972, 1973 time frame. We hit the peak, went over the peak in 1973, and what did OPEC decide to do? OPEC said, okay, the U.S. has shown us what their peak is, and they've shown us they're on the downturn. We now control the amount of oil that's available to the world, and therefore we control the price. And that's what OPEC saw. You can see there's a little bit of uptick in the 80s. That's a lot of offshore work. The onshore trend continued down and continued down to about 5.5 million in the 2005 through about 2009 time frame. And so what happened at that period of time for oil? When unconventional resources were started by Mitchell, basically in the Barnett play, we geologically sat down and said, well, you know, we've been looking at source rocks, and Tony probably with I have been looking at source rocks for decades that are now playing as unconventional rocks. And we love the source rock. We knew over geologic time we migrated oil. About 25% of the oil that gets generated out of source rock migrates out. About 25% of that is captured, and then we end up producing about 20% of that number. And I've done those kind of studies in many of the basins in the Gulf of Mexico, in the correlation between what's been produced and using just those general numbers, 600 barrels of oil per acre foot per 1% TOC, and then measuring the source rock and using those simple ratio numbers has a fantastic fit for all the onshore Mesozoic basins in the Gulf of Mexico. Well, we've gone back to so anyway, we saw how methane would move through those rocks, but at that time, nobody thought we could possibly move hydrocarbon chains through any of these pore throats. Well, surprise, surprise, it started in the Bakken, and the Bakken is really not, and It depends how you define unconventional resource play. There's two general definitions. If you drill horizontally and you frack it, some people call that an unconventional resource play. And I guess that's a good engineering definition. I really kind of think of it more as a source rock play. And if you use that definition, the Bakken is really not a traditional unconventional resource. It's a transitional play because it's sandwiched between the source rocks. And we're playing a very moderate porosity, very low permeability, tight unconventional resource play between those two. And if you look at it, as a matter of fact, if you take Fred Meisner, who worked for Shell, if you take his paper that he wrote on the Bakken in 1978, and that was a paper on the organic geochemistry of the Williston Basin in the Bakken, you would find every high producing area in the Bakken that was produced. So it was amazing once we got to that level of discovery and going back and look at Fred's great work. But this is what we've done. We're currently producing a little bit over 12 million barrels a day, so we more than have doubled from the unconventional resource plays. As a matter of fact, this is, again, looking at total production during this century. In the green is the unconventional oil contribution. So it starts out at a very low percentage of our total, which you can see went down to about 5 million, 5.5 million in the late 2000 time frame, and that unconventional resources were less than 10% at that time. It's now 60% of total oil production in the United States. So if we just look at the tight oil, we'll see that the blue is the Eagle Ford, the brown is the Permian, the yellow is the Bakken. So let's just look at those. The other ones are on there. You can see it started in the Bakken, and the yellow starts increasing first back in the 2005 time frame. That's when most of the development drilling was going on in the Elm Coulee field. And then it moved over to the North Dakota area about 4 years later. In about the 2010 time frame, the Eagle Ford starts coming on. But since 2015, most of the addition has been from the Permian Basin. You can see that brown increasing in there. Well, the Torah research started about 12 years ago from the Sloan Foundation. Some articles were started to appear in the Wall Street Journal. It was actually a geologist that was quoted, who's a member of the Houston Geologic Society, and that's as far as I'll go, who told the Wall Street Journal that there were 100 years of gas reserves in the unconventional resource plays in the United States. So hearing some of that for the first time, the Sloan Foundation came back to the Bureau and said, can you go back and study these basins and plays in detail? And at that time it was all about the gas. And tell us how much is coming out of each one of the gas resource plays. So you'll see there are three sets of bubbles next to the Marcellus, the Barnett, the Fayetteville, and the Haynesville. The first bubble is oil in place. That calculation we looked at, and that's built from the ground floor up on looking at all the geology. The next bubble is technically recoverable. And everybody asks, why do you look at technically recoverable? Well, technically recoverable means I could actually go get it with a drill bit. But how much I'm going to get is dependent on economics. So we look at technically recoverable, and the percentage of the technically recoverable bubble that we get to is dependent on two things: the density of the hydrocarbon, and then the economics of getting that hydrocarbon out. So you have to tell me what economics you want to use first, and then I'll tell you what the density is, and then we'll figure out together how much of that we go get. And then the smallest bubble, excuse me, every time we get these fronts coming in, the allergies kick up. The smallest bubble is how much had been produced at the time of each one of those studies that was done. So the gas bubbles there were all done as part of the Sloan Foundation studies. Torah continually updates those, by the way. Then when that was completed, the DOE in 2010 time frame, a little bit later than that, came to the Bureau and said, okay, you've done the Sloan Foundation, we have a copy of those reports. Can you start looking at the Eagle Ford and the Bakken? Because as you saw from the previous chart, those were the first two that really kicked off. And so we did those studies. And then we've, a couple years ago, when they were completed, I think Scott Tinker, the director of the Bureau, probably had a 30-second conversation with himself and saying, okay, are we going to go ahead and do the Permian Basin? And of course, being the Bureau of Economic Geology for the University of Texas and the state geologist for Texas, we were going to look at the Permian Basin. There's a lot of research that we have at the Bureau on the Permian, obviously. So when you look at those green bubbles, though, don't be surprised. These are in actual units. So the gas is in MCF and the oil is in barrels of oil. And so if we looked at the energy equivalents, we'd have to blow up those green bubbles 5.6 to 1 versus the gas. If we use the SEC regulations, we'd use 6 to 1. If we use the economic equivalence over the last 30 years, we'd use a 10 to 1. And if we use the economic equivalence over the last 10 years since unconventional resource plays, we'd have to blow those green bubbles up 23 times versus the red bubbles. So if I did that, this diagram would look like what? It'd be green. That's all you'd see. So don't be surprised at how little that is. And what we're showing you there in the Midland Basin is an estimate for the entire resource there. The interesting thing about the Midland Basin is if I put the gas of the Midland Basin, the only gas resource that would be larger than the Midland Basin would be the Marcellus. And we're doing the Delaware Basin study. The Delaware Basin study should be released at our fall meeting, which is going to be in November. The Delaware Basin has much more hydrocarbon in place. The basin is 1/3 larger than the Midland Basin. The stratigraphic interval is much thicker, and the concentration of hydrocarbons is much higher. And it's a lot more diverse also. But that bubble is going to be much larger than that. So if you combine the two, then we have a bubble that's probably at least as large as the Marcellus. And then we can start looking at infrastructure. You know, why do we have so many problems in the Midland and the Permian Basin right now? We're producing as much gas almost as the highest potential gas resource play. And we're doing that out of oil play. So that's why there's so much of a problem. And we look at the infrastructure. We're currently working with ERCOT to see if they want to join the consortium there. So we're going to look at the oil here, and the black histogram on the far right is the current annual consumption in the United States, 7.9 trillion barrels of oil. Those green bars are the green bubbles you just saw on the previous map on there. So just those resource plays alone have 23 years of resources in them. If we look at the gas, again, the white histogram on the far side is the gas consumption, about 31 trillion cubic feet of gas that's consumed in the United States. And that's the amount of resource that we're getting out of there. So you can see that Midland and that Delaware histogram almost as large as that Marcellus histogram over there. And that's about 50 years worth of gas for North America. Of course, we're not going to use it all in North America. We'll export a lot of that. So there's global oil production now. And the little green ribbon on the top is the U.S. production and worldwide production. You can see we're not only increasing in the United States, there's a lot of great exploration going on all over the world. You've heard that the last couple of years there have been a lot of negative reports about how much oil and gas we're finding. Look at that diagram. There's a lot of oil coming online over the last couple of years. We've looked at that graph before and that graph. So here's U.S. production. As we said, this is stretched out a little bit from 1965. Again, you can see it drop, and you can see it rising up to about 12 million a day. And there's total consumption, so the light green then is the result of the imports. I don't know why I keep seeing articles that saying we're energy independent today. We're not. We've done a lot to abate that, but we're not independent at this point. All right, let's look at the perfect unconventional resource play. And here's what we're going to do in looking at that. We're going to take all the results from Torah, and we're going to look at this financially. And we're going to take all the information that we have in Torah and all the information we have from all the oil and gas companies. I'm going to take all the knowledge of all the wells. We look at every unconventional resource play well every month. And we're going to look at all those results. But I'm going to go back to time zero. And time zero in this case is not a single unconventional well has been drilled yet, but I've got all that knowledge. So knowing that and being able to go out there and do anything I want without any competition, what would I do and how would I accomplish that? And that's what this perfect unconventional model is. Just point out, most of the economic models that has to do with optimization has to do with how much of a particular project I want to take. What we're going to do is say, how much of my total capital should I spend on particular projects? A little bit different look at doing that. These optimization models have a lot of variability in them because it relies on the risk tolerance of the individual evaluator and all the managers in the firm and the firm risk tolerance. And guess what? All of those change every day. So the perfect answer that you might get in these 10 minutes will probably change by late in the afternoon, let alone tomorrow morning. So those aren't good answers. All right, these are the oil resource plays we included, and these are on quintiles. If you know what those are, that's great. If you don't worry about it. Those are the oil EURs for every well in the oil plays that we're going to include here, the Bakken, the Eagle Ford, Niobrara, and Permian. So I don't have every resource play in there. I don't have the Oklahoma mid-continent resource plays and a couple of the other Rocky Mountain ones in there, but we have a good representation of them. And here it is for the gas plays and what we looked at. Well, in those using quintiles and using the tail ends of that, you can see there's some errors in that. So I just go back to my old Pete Rose methodology and Al Capon methodologies, and I plot them on log probability paper. And here's what the plots for those basins look like on log probability paper. You can, over on the left-hand side are the oil plays, the right-hand side are the gas plays, plotted at a 10-1 ratio. As we talked about, that's kind of the long-term economic equivalence of those, so you can kind of see how those compare. And the other thing that kind of surprised me when I did these is how uniform the slope of those is. So that means there's a uniform risk is the amount of oil that would be produced out of each one of those plays. You can see in the oil there's one exception, that's the Delaware Basin. And you can see in gas there's one exception, and that's the Utica play, both shown in black. So to define the perfect portfolio model, I've got in the Permian Basin there are over 10,000 horizontal wells that have been drilled. Do I have to do economics on all 10,000 wells? The answer is no. I only need to do it at the P50, the P90, which we get from those plots, and the expected value. So the P50 and the P90 are very easy to determine. The expected value is a little bit trickier, but what we can do is we can go and we can see just read off the P50 and the P90. I do economic run what those numbers are, and that's really easy to do. To get to the expected value, because these are log normally distributed, and even though you learned in your first statistics class that most things in nature have a normal bell-shaped curve, that's not truth. Most things in nature are log normally distributed, especially the factors that we work with. So these log normal plots are fantastic, or log probability plots are fantastic to be able to take a look at. Two methods of doing that. The one on the right is the algorithmic solution, Swanson's mean, 30% of the P10 and the P90, and 40% of the P50 gets you the expected value number. And then I always check that with these plots that you can do to come up and tell you what probability number the expected value is, and that's where the expected value is on those various plots. So I only have to run economics on 3 cases. And so why Shell is over there, Tony, all night doing Monte Carlo simulations. I'm using my PC and I'm plotting out 3 cash flow models and coming up and being able to estimate what these projects look like. Now, when we look at economic variables, and this is an interesting item to look at. Once we come up with our geologic answer, then the engineers and the finance guys are going to start asking us questions like, what should my well spacing be? What kind of packing should I use? Or what kind of pattern should I use on my drilling? Well, guess what? You can't come up with, there is no perfect answer. Because if I'm a mineral owner, the answer is that I want you to drill a well 100 feet laterally and 100 feet horizontally from every previous well. Why is that? Well, I don't care how much capital you spend. I want you to get every drop of oil that you could technically possibly get out of there, but that's not the good economic answer. So then, well, all operating oil and gas companies have the same answer, right? No. Some companies are interested in return on investment. Some companies are interested in building wealth. So you have to know what the answer is for your company to be able to answer that question properly with the engineers for your management and for your investors. In this model, what we're going to use is we're going to use investment efficiency. And investment efficiency is also a discounted return on investment or profitability index. So if you hear any of those terms could mean essentially the same thing. I could have done it on return on investment, internal rate of return, but this typically is the best measurement to be able to use. So if I put these and I do them by investment efficiency, then these are the investment efficiencies in ranked order of the expected value for each play. And so you can see how they rank there, and then I've got a nice red line across there. Well, we're using discounted cash flows, so let's say we discount these at 10%. I'll talk about that on the next slide. And if I discount it at 10% and I get a return of 1, it means I spent my capital, and then I spent several years of expensing my LOEs and any additional work I have to do on the well, and I'm getting a cash flow back, but that discounted cash flow equals the amount of my original investment. That's an investment of 1. So if you get an answer that's less than 1, don't make the investment. As a matter of fact, you should use an investment efficiency of 2. So if the answer is I should use investment, and by the way, the cash-on-cash answer is 3. So if my expected investment efficiency should be 2, my cash-on-cash should be 3, and my best play is a 1.5, of the tens of thousands of wells that have been drilled on unconventional resource plays, you would probably only drill the upper end of each one of these plays. That's the answer. And so you're hearing that over the last year, and why is there so much pressure on the unconventional resource companies? That's the reason why. Now, I'm going to give you good news at the end. So there's a little bit of a downer. The good news comes later. But if all I'm going to do is evaluate them on efficiency, and as a matter of fact, I did this with Petrohunt. When I first went in at Petrohunt, I evaluated every potential well we were possibly going to drill. I did the proper risk weighting. We did the cash flow models. I ranked them by investment efficiency. So when senior management said, okay, where do we start? I said, we start at the top of the list, and we just drill our way down until we run out of capital. And so that would be the answer here. So the answer here would be is you would drill all your Bakken prospects till you're done with your Bakken, then you go to the Delaware Basin, you go to Marcellus, Eagle Ford, Midland, and then you stop, given this answer. So I've already mentioned about using an investment efficiency of 2, cash on cash, that's undiscounted, of 3, and now I want to talk about using PV10. Because industry-wide, we all evaluate our projects, whether we're an engineer or finance guy or a geologist that knows a little bit about cash flow models, we use a PV10. Well, why is that? Well, why people that are looking at different companies and people that are within the same company that are looking at different regions or even in the same regions looking at different prospects, they want to be able to evaluate it all at the same PV number. Well, that's not the right number to use, and I think I've got this on the next slide. And why is that not the right number to use? Because the right number to use is what your company's cost of capital is. So let me take a really good case first. So if I've got $1 billion in the bank, and all I'm going to do is let that money sit in the bank, and the only investment opportunities are the exploration projects that we bring forward for oil and gas. And so my choice is drill the oil and gas wells, or let the money sit in the bank, and let's just say I can earn 2% interest. You probably wouldn't even earn that today, but let's say we can earn 2% interest. I should be using, what's my cost of capital? 2%. Because my option is keep it in the bank, let it earn 2%, or drill the oil and gas well. Well, because sometimes you look at a private family company and you go, how did they possibly pay that much money to buy that asset? I thought it was worth $1 billion and they paid 1.5. Well, their cost of capital might be much different than what yours is. Now, 10% might be good for a public company if they're 100% equity, but most public companies aren't 1% equity. So let's look at the other scenario. So the other scenario is that you get your money from a bank, and you're not getting it at prime plus 2, you're getting it maybe at 14%. You're getting it from a PE company, and if you look at their formulas, it's usually about 14.5% up to 16%. It's 14.5% if you don't count the fees. If you add their fees in there, it's about 16%. If you look at mezzanine financing, it's between 18 and 20%. It can get up into the lower 20s. Well, what's the risk of actually having cost of capital? And this is, I think, now we're going to blame the finance guys. And here's why we're going to blame the finance guys, because if you evaluate a project at PV10 and the actual discount value should be 14 to 20%, that means that you are going to pay way too much for some of your assets. And you're going to make investment drilling decisions at a PV10 that you should not be making because you're never going to make the return to what your investors are going to expect. So almost every PV, and I've worked with a lot of PE companies, we've always used a PV10. And so they're blaming us for underperformance. They need to share the blame. Said, okay, you should have been using a 14.5 to a 20% discount. If we would have been doing that, there were a lot of wells that have been drilled, tens of thousands of wells that have been drilled that would not have been drilled had that company's proper cost of capital been used in this equation. So that's enough of the bad news and where we're going to go with blaming. So we're going to use these numbers. I've already talked about using the slope and the expected value number. So here's how we construct a portfolio, get a little more advanced than just using investment efficiency, is the first thing that I need to know what the variability of my potential outcome is. And that it's the formula on the bottom, and it's really pretty easy. So listen to me rather than look what's up there, because when I look at it, it looks kind of complicated. So you take your PV10 case, your high side case, you subtract your PV50 case, you divide that by your PV10, and then you divide that by 1.28. Okay, so that all, the PV portion of that makes sense, right? You take the number, you subtract them, you divide it by the result that you want to exceed, which is the PV. And the 1.28 is because we've plotted these on log normal, we've made a normal distribution out of it. That's the distance of the Z values, or the distance, standard deviations between PV50 and PV90. So you divide it by that number, and that gives you what the standard deviation is. And the plot of the financial, so what we're going to do is we're not going to plot drilling results. We're not going to plot production results. We're going to plot these metrics that we're looking at, and we're plotting the expected value numbers. And so that's a plot now, and you can see that the Bakken, if we look at the y-axis, you'll see the investment efficiency. Remember, the Bakken was 1.53, and then the Delaware and the Marcellus were above the Midland. But look at the Midland Basin. The variable outcome on the Midland Basin, the standard deviation, is so much lower than it is in the Delaware and the Marcellus. Is there an advantage there? Yes. The lower the standard deviation, the more certain I am about the outcome, the more certain and more comfortable I can make my financial investment community, because they're much more comfortable about the return. Well, how do I decide what to drill out of that scatter plot? Well, it's really easy. If I'm going to look at the y-axis and I'm going to look at a Bakken and a Midland well, and I drill 50% interest, or I take 50% of my capital budget and I put it in the Bakken, I put it in the Midland, the Bakken's going to give a 1.53, the Midland's going to give a 1.14, so it's just a straight average of 1.34. So that's the expected outcome. Now I want to look at the standard deviation. The standard deviation is a little bit trickier. It's actually the mean square root of the standard deviations. And this is the magic of portfolio construction. It's the mean square root of my project risk. And so I won't go over all this, I'll just show it to you on a picture. You can see now what I've developed is, all I have highlighted there is the envelope on which all the answers exist. So there are millions of possible answers within that envelope, but I didn't fill them all in because I wanted you to see where our particular basins and our particular play still sat on there. But if you look at drilling, for example, the difference between a Delaware and a Bakken well, you'll see how that curve in the standard deviation is less than the lowest standard deviation. It's not an average. I can actually get a standard deviation that is lower than those probabilities. And so every dot now within there represents a different percentage of each one of those different plays. How do I figure out of a million choices which one of those to do? It's really a little bit more straightforward than that. You'll see in orange, what I've plotted there is the highest and the lowest outcomes at the lowest standard deviation, is that outside envelope that's shown in orange. Everything else, the envelope on the right and everything in the middle, would be colored gray. Well, here's that upper part of the orange, which is called the efficient frontier, or the efficient set. And what that represents is, that's the highest potential return at any given standard deviation. Or at any given standard deviation, it's the highest return I can get. The one in red, that's where you cut it off on the low end. That's called the minimum standard deviation portfolio. That's the lowest standard deviation I can get, but you can see it's not the highest return. So again, how do I pick on that particular envelope what to do? Because you'll see it's not just Bakken and Midland in that play, there's a series of them. And what you do is you draw a straight line which intercepts your zero risk investment. Well, my zero risk on this is 1 because I'm using investment efficiency. If I was using internal rate of return, I might say, well, the bank is the safest place, or maybe a T-bill where I'm going to get 1.5 or 2%. And you'd use that as your y-intercept. So you draw a straight line and you intersect that upper slope of the efficient frontier or the efficient set. Well, mathematically, that P star then comes out to this portfolio. Instead of drilling all my Bakken plays first and then going down to the Delaware Basin, look what happened. The Midland jumped from 5th to 2nd. Now, that as far as the total percentage. And these are the percentages, so these numbers should add up to 100. And this is not how much of a Bakken prospect I should take. This is how much of your capital should be spent in each one of these various plays. So you would go after the average or expected value Bakken, then the expected value Midland, and you drill 45 and 29. And then you see you get a little bit of Delaware, a little bit of Eagle Ford, a little bit of Marcellus mixed in there. Well, this slide shows, again, the expected value numbers next to those first 5 plays that we should represent. And then what I've put in there is what the industry has actually done, the percentages of wells they've drilled in each one of these plays. And this is, again, only looking at these 10 plays, not all the wells that we've drilled over the last 10 years. And the percentage of capital. So you can see that the percentage of capital for the Bakken is lower than the percentage of wells. That means the cost of the average well is lower than the overall average of all these 10 plays together. Let's find one that varies the other way. Look at the Delaware. The percentage of wells is lower than the percentage of capital. That means in the Delaware you're spending more money than the average unconventional resource play. So let's look at the Delaware. We should spend 9% of our capital. We actually spent 13 to 15% of our capital. That's the closest one. You can see in the Bakken, the Midland, they are underrepresented of what versus what we should do.
Bill, is that Delaware case because of the external cost, high cost of acreage, high cost of operation, high cost of services?
These are the cost of drilling.
Just
only. So
drilling only. Okay, just checking.
Which is a really good point. Finance guys call that secondary cost. So we're only looking at secondary cost here. We're not even looking at entry cost here. So if you've paid $6 billion, Exxon, for, and I'm not picking on Exxon, but for example, just the first one that came to mind, that $6 billion is not in these calculations. That they should be, which would make these expected values even lower. So you can see why the finance people. So the point here is that the plays that we should have drilled more wells in are underrepresented, the Bakken and the Midland, and that the Eagle Ford and Marcellus are overrepresented, and the Delaware is the only one that's close to being right on line with what we should have spent. So, regardless of your risk tolerances, every firm should pick P star. Okay? Regardless of what I think individually, what my managers think, what my investors think, everybody picks P star. I've eliminated individual risk here and corporate risk by doing this and looking at, because I'm only looking at returns. So where should I go if I don't want to accept that return with that given risk? Well, the only place I can go is within that envelope, with one exception. But if I want a better return and I want to go up that orange curve, look what happens. I'm marginally reducing my return for risk, so that's unacceptable. I'm getting better return, but it's a marginally reduced rate versus the P star. And then if I want to do less risk and I want to move down, could I go down and to the left? Well, as I do that, I'm lowering risk, but I'm greatly reducing my return, so that's unacceptable. So the way that you get, if you want something higher, is I now move along that straight line. So if I want to take more risk and I've got a $2 billion drilling budget, but I want to spend $4 billion. Well, what do? My company's only giving me $2 billion. Well, I go out and I borrow from the guy that didn't want to drill as much at a PV10, because that's what everybody in the industry uses, and I borrow at 10% interest off that number and I go drill more wells. So you move up that line. Now look what's happening. I'm moving up a straight line. So I'm getting additional return, but I'm taking additional risk to do that. If you want to reduce your risk, move along the black line, because you see wherever I end up on that black line, my return is higher for every level of risk on that particular portfolio. So my management's giving me $2 billion, but I said, well, what I really want to do is spend $1 billion on capital investment, and then I'm going to give you the other $1 billion, and you're going to pay me 10% back. That would be the idea of moving up and down those. So that's how we construct it and use it. So let's look at some good news, because that's all. A lot of what you're hearing is that we've spent too much capital to get the amount of hydrocarbons. So the first good news we saw is, boy, have we impacted the U.S. production. Let me mention something I didn't mention in that introduction guide. I just thought about this should be mentioned. For 150 years, this country has beaten the rest of the world because we have the human capital and we have an educated human capital with imagination to go out and do a lot of great things. But to do those great things, we needed low-cost energy. We have the lowest cost energy. There's a very close relationship between energy usage, GDP, and wealth. We've got some of the lowest cost resources in the world. So when pioneers first came over here, what was the lowest cost resource? It was all the available land. There was risk associated with it, but it was low cost, and it was forest, and it was a lot of animals. So that was their food, that was their shelter, that was all the resources that they needed. For the last 150 years, it's been oil and gas. Oil and gas is only 4% of the GDP. It used to be about 6 to 8%, but it runs everything in the economy. So our production going from 5.5 to 12, we have provided the rest of the U.S. economy with, now we haven't gotten credit for that, we haven't gotten the money from doing that, but we've provided that for the entire U.S. economy to run the way that it has. Now, Scott Tinker expands that even further if you've heard some of his talks. He said by doing that, the only way to lift people out of poverty is to provide low-cost energy. We've done that. So even though our companies aren't performing as well, even though we've had hard times at our jobs, everybody should feel good about what we've done for the U.S. economy and what we've done for the world, because the only way to lift 2 to 3 billion people out of extreme poverty is to give them low-cost energy. And we've done a big part of being able to do it. So that's the other good news associated with it. And we've gotten a lot of criticism about the amount of capital that we've spent to do that, but there's other good impacts associated with doing that. But let's look at an individual company using that same data and information on a basin play, and that is the industry-wide, so that's the macroeconomic level. So now we're going to go to a microeconomic level. Can an individual company do better than the industry? And the answer is yes. And I'm going to show you examples of some of River Ford's capital budget here. And so this was, on the left-hand side, River Ford's evaluation of some of the opportunities that it had available to it over the last couple of years. Same type of plots you can see on there. And the point I'm making is that those plots, the averages and the total numbers are better than the industry plots. Well, are they wrong? No. If you're sitting in the middle of Cooley Field, you're sitting in the middle of the Delaware Basin, you might have better opportunities than the industry does in those particular areas. Is it possible that you have worse opportunities than the average in the industry? And the answer is yes. But unless you've done the type of evaluations that we've done to be able to say, where is every drop of oil in the middle of the Permian Basin, you don't know what that answer might be. So these are possibilities. I just wanted to show you how those plotted on there. I do want you to notice that one slope that goes way down and to the left on River Ford's choices, those are Cooley infill wells. Because there's certainly a risk when I drill an infill well 7 or 8 years later that my lower end reserves might be significantly lower than what the original wells were, and that's what. So I'll show you those results in just a minute. So if I plot those opportunities on there, so now in light gray you can see what the original opportunities were, and now you can see what I thought River Ford's opportunities were, and you can see the investment efficiency y-axis has changed. I've doubled the size of that. And you can see there's some significantly different returns. Now look at the average Cooley infill drilling well, and that's where I really thought it was, but they're obviously very low risk wells to drill. So the light gray portfolio is the first portfolio we looked at. The orange portfolio shown there now, and P star is only the portfolio with those opportunities in the upper portion of the diagram. Also mentioned, because we're going to look at it in just a minute, is a portfolio that uses both of those things together, but I didn't want to get this graph too confusing on there. So there's P star of what River Ford should have done. I did this post drilling as far as this result is concerned, so I'll show you how that worked out. Well, if I use over on the right-hand side just those three choices, that's the percentage of capital that River Ford should use to spend given these models that we've taken a look at, the perfect exploration portfolio. And it's just because we already had a position in the Delaware Basin that we were able to drill 2-mile long horizontals. The other part about 2-mile long horizontals is that we're fracking them much better than we did a year or 2 years ago. A lot more stages per 1,000 feet, a lot more perforations per 1,000 feet, a lot more proppant, and at much higher rates. So that's in these numbers, but those are some of the details that are down below that. There are still some 1 mile horizontals to drill, and then the Coulee infill wells. Over on the left are the choices, if I can choose from the combination of both those portfolios, that I ought to do. Well, you can see they're generally the same rank order, but it gives me a lot more variables and a lot more choices if I can do all of that. Now, most companies won't have the technical expertise to play each one of those basins and plays. They might have a corporate edict that they won't make all those plays, but those would be the best choices if everything was equal throughout all of those. So an individual group might say, well, I'm a Permian Basin player only, and I've got the best acreage in the Permian Basin. Are you going to do better than the average player? The answer is yes, you're going to do better than just like you're going to see with these results. So this is a little confusing, but let me kind of walk through it again. Over on the left and the middle are the portfolios that we should do if we had all the choices on the left, if we only had the upper choices in the middle, and then what we actually did as far as our capital spend. So let me start with number 1 over on the left. Because we had a previous position in the Delaware Basin, that allowed me to go up to number 1. The models say that I should drill between 50 and 92% of my capital ought to be for these Delaware Basin, both the 2 mile and the long and the 1 mile. I actually spent 90% of my capital in the last 2 years doing that. Number 2 is you see 14% should it be in Bakken, 5% of that should be these Coulee infill wells. Well, again, because I had a position in the Bakken, and look at what decisions I made, and this was looking back, so I actually wasn't using this model at the time. But the decisions I made is, I said, well, I'll spend 6% of my capital, and I'm all non-op, so I have to wait for somebody else to come in and propose those. Drilling the Coulee infill well, so I approved all those. And then I said, I should be represented up there more early. I was talking with Tony earlier. Spent most of our capital in the southern Delaware Basin. They're great numbers and great results. But economically, my best return wells are the Bakken. Just like this model said. My lifting costs are lowest, and my return is the best. So I said, I need a little bit more of that, and went out and bought a little bit more Bakken. So even though I didn't have this model, intuitively, I was kind of using this model along the way. And those are the results there. And so in Coulee, I purchased some additional PDP in the Coulee field. I drilled and completed the 2 mile long and the 1 mile long horizontal Delaware. And I drilled and completed the Coulee infill wells. And all of those, up to the Coulee infill, came in right as we predicted them. Now the Coulee infill wells didn't come in as predicted. They were up and to the left. So the risk was lower and my return was higher. And so when I look at that particular curve, and you can see I have 2 circles around it, my results ended up between the P50 and the P90. I didn't have any results below the P50. Well, if I drill a couple wells, that shouldn't work, right? Well, there are 2 issues there. Until I've drilled 30 wells or I've done 30 capital investment, I really don't have a statistical valid sample. We've drilled fewer than 30 wells, so it could be that I just haven't drilled enough of them and I haven't drilled the bad ones yet. And it could be that that curve, like the right-hand diagram shows, should be back up where the original Coulee was. Because remember, I've got a half-mile spacing in the Coulee field. And so if I infill in a 1/4 mile, maybe I do have virgin reserves to capture in there. So here's the question. The geologists and the engineers that worked on the Coulee, and that's one person, underestimated what the Coulee was going to do. And my financial performance was superior to what I predicted. Should I reward the geologists and the engineers? Should I reward the geologists and the engineers? I don't see any heads turning any which way. Well, there isn't a perfect answer on that one. You might say the easiest thing to do is everybody's doing great. We did better than we expected. We're going to have a Christmas party, and we're going to give everybody a little bit of a bonus. But I didn't correct the problem. And the problem might be that my geologists and engineers didn't evaluate that properly. And because they didn't evaluate it properly, and it actually was better, if they would have predicted it would have been better, maybe I would have gone out and purchased more Bakken properties, and maybe I would have looked for more infill drilling opportunities in the Bakken. So if that's the case, I'm going to say, no, I'm not going to reward them, and we're going to have a new class on how to estimate parent-child relationships, and we're going to have some kind of higher number. So what the right answer is, that's up to everybody to decide, but since I'm a one-person company, I went the way of not paying bonuses and evaluating the process.
One key question, please.
Yes.
As one of your potential employees or an individual often in that position, was the data available for them to have made that evaluation?
Yes.
On the company's behalf?
Yes.
Okay.
Yep, they had everything available to them that they needed to make that evaluation, they being me. Yes. All right, so here's industry trends and improved capital performance. I just wanted to show this up because this is the other good news that we've been criticized for, and this isn't a study per se, this is just the results in the Midland Basin side. And the Midland Basin unconventional resource started about 3 to 5 years before it did on the Delaware Basin side. But as of about 2 years ago, there have been more horizontal wells drilled in the Delaware Basin than there have in the Midland Basin. The Midland Basin is 2,000 feet shallower, it's normally pressured. Remember, the results are a lot less variable. The Delaware Basin is deeper, has higher pressure gradients, has higher initial better results. And so those are just some of the overall differences. There are a lot more heterogeneities in the Delaware Basin side as far as the geology is concerned, the pressure is concerned, the basin history is concerned, therefore the basin modeling is much different. And a lot of people don't understand why they're getting the results that they are. Why are they getting so much gas? Well, why are they getting so much gas in the sweet spot versus why are they getting so much gas on the margins? There's different reasons in different places in the Delaware Basin, and we're evaluating all of that. But if we look at the Midland Basin, and so the point I was going to make in the Midland Basin is that 50% of the wells have been drilled in the Wolfcampian B, 25% of the wells have been drilled in the Wolfcampian A, and 25% of the wells have been drilled in one of the Sprayberry zones or one of the deeper Wolfcamp intervals. But if we're looking at just the A and the B results today, that's these histograms, and as capital efficiency along the x-axis, sorry that's hard to see, you can see a number 1 just to the left of that dark line going straight up and down on the x-axis. Well, that's a 1 return on capital efficiency. Remember, I want to be greater than 2 to really make the investment decision. So in the 2012-2013 timeframe, when we were generally drilling 1 well per section and we were drilling 1 mile long horizontals, we're basically right at a 1 capital investment return as an average. And the distribution was much tighter. And so if you go towards 14, 15, and 16, you can see those 3 are kind of grouped together at about a 1.6. And you see the distribution is moving to the right. There's greater variability, but most of that variability is positive outcomes. So it's moving in the right direction. And then finally, what color is that? Purple? Magenta? Let's go with magenta. That's a greater, better sounding word. Magenta is actually about a 2.2 on average with many more positive outcomes. So the trend is it's all moving in the right direction. So some of it is that you'll hear, well, we spent all this capital, but yes, we're getting better returns. Now, are we getting better returns because we're just focusing on the acreage? That's part of it. We have less capital spend than we had a couple years ago. But I also think it's in the completion efficiencies. I've heard finance guys say, oh, you've hit the limit on completion efficiencies. And most of the plays I've looked at, the answer is no, we haven't done that. But that's where we are. So 2 bits of good news versus the overall model. You can do better, as you saw from the example Company X. So outside this room is Company X, but you all know who that is. What's published says Company X. And your company can do that when you make good choices and you're in the right rock and your engineers do the right kind of completion. So that's good news number 1. Good news number 2 is the trends I'm seeing, even at low prices, are showing that we're moving towards better and better capital efficiencies. So that's how we build the perfect portfolio, what we should have drilled, what we've actually kind of drilled in those, and different ways we can beat it, and some of the great things that the people that are working on conventional resources have done, not only for this country, but also for the world and providing this low-cost energy. Thank you. So Scott got his questions in along the way. Does anybody else have some questions? And if they don't, Scott, you can ask one more.
Thank you, Bill.
Okay.
Sure.
Thank you for the presentation.
Mm-hmm.
If I want to take a message from this presentation, I think I have two messages that I want to take, that I want to double check with you.
Okay.
So one is, in all these fields, we drill a lot of wells that we shouldn't drill. That's one thing that I am
Yep.
taking out of the.
Yeah, overall, the capital that we've spent.
Yeah.
So that's why I wanted to stress two things. The oil that we've gotten out of the ground and the increase in production has done a lot of good things outside our individual companies and outside our industry. So we all need to feel good about that, but that's a feel good. That doesn't put money in our companies' pockets. And when we look at our companies, what we have to say is, on average, we've spent way too much capital for that return.
Okay. And then, the other measure that I am kind of getting is that when this kind of model that we are able to do now, we can have a better idea in terms of efficiency. And then that two number that you get in that, like, if I see that two coming, I say, okay, I can do my investment in this kind of projects.
Yep, you can say,
These kind of fields.
you can say, look, Wall Street, who doesn't want to invest in oil and gas right now? You can say, look, I feel your pain. I agree with you. Here's a study that says that I agree with you, but guess what? I'm going to do much better. So I think the way to do that is to say, I can compare not only my acreage position, but I've got the subsurface, grassroots subsurface data and information that shows that I'm in a much better area. And I can show my engineers they can get better completions. And then finally, I've got the economist and finance group that's going to show you that we're going to get better returns than everybody else. Is that possible? And the answer is yes. It's very possible. I've shown you an example of how you can do that.
So, thank you, Bill.
Mhm.
That's great.
Charles, I promised you it wasn't going to be the typical geologic talk that you've seen 14 times before.
Yeah, no, it's always great to sort of think about optimization and using the data. So I'm just thinking about how the industry is segmented. So there's independents, there's international oil companies, there's national oil companies. So any comments about the business cycle and how different companies approach for them the optimal portfolio?
Yeah, and Charles, we could spend a whole semester using just these charts and graphs and talking about that one particular issue. I've always enjoyed working for companies where we had the opportunity to have divisions in multiple different regions. I always loved to have properties in the onshore and mostly onshore Gulf of Mexico. High porosity, high permeability sandstones. Okay, high return on investment kind of projects. The problem with them is I've got to reinvent the entire division every 3 years because those things that I drilled 3 years ago might water out, and so you have to keep doing that. And I always loved the Rocky Mountains and the Paleozoic plays. My initial returns weren't as high, but they were lower risk, knew where the hydrocarbons were, and then the production tails were just long, steady, slow production tails. So that's possibilities. The other one is if you're a PE company, and the PE and your investment company is going to say to the operating arm, you got to find a county in one play in one basin. Well, is that a bad thing? It makes me nervous because they're going to do the portfolio risk. They're going to have 20 companies in the Permian Basin. They're going to have 10 in the Bakken. They're going to have a couple in the Mid-Continent. So they don't want the individual asset teams to do the diversification. They're going to do the diversification themselves. So the answer is, if that's the situation you're being put in, you better know that basin and that play really well so you can end up on the top end of those distributions. And you got to know that before you get the funding and then before you go out and make the investment, as opposed to a large international firm or a well-diversified domestic firm who's got plays and assets in several basins. They can turn those buttons on and off. So it depends who you are, Charles. what your company is made up of, how big and diversified they are, versus how focused you have to end up being.
So just to follow up, so what about the global turn-on? So this is great. This is the Fertile Crescent, if you will, U.S., North America. So what about the rest of the world? What can they take from this? Because they haven't quite gotten as far as the U.S. has.
Right, but remember the worldwide production curve that we looked at before? And the U.S. was just a little ribbon on the top of that, and our numbers have come up, but look what we've done internationally. And just as an example, ExxonMobil has offshore Guyana. They're finding huge fields with great production rates out of the individual wells. The numbers that I think maybe some of us heard were that Guyana is going to go from one of the poorest countries in the Western Hemisphere to the second wealthiest per capita country in the Western Hemisphere, just from the result of what ExxonMobil has. So there, if your choices are, I drill some of these now trend wells with discoveries I've already made offshore, versus do I spend that same amount of capital doing an unconventional resource play? I think what we're seeing in the international arena is, as long as I have low-cost traditional plays, like we had in the United States for decades, and then what happened is that was trailing off. Well, as long as I have those kind of investment opportunities, if I put those risk-weighted properly in the same portfolio, they would have many times higher investment efficiencies. And then I don't know what the risk would be, but the point would be is your capital decision would be go after those offshore fields in Guyana every time. So the unconventional resource plays internationally won't be played until more countries have exhausted their current existing traditional resource traditional resource plays. So that's why, Charles, we haven't seen it international so far. The United States had no choice. We were out of investment opportunities. We weren't out of opportunities. Marginally, we were out of opportunities. There's still opportunities out there in traditional resource plays. But to replace our national production, we had to go to the unconventional resource plays to do that. And those were the only choices we had. Thank you all very much.
Thank you, guys.